Hello everyone, the topic of my presentation is optimal control of storage under time varying electricity prices. Conventional power system has fossil fuel based power generating resources which were completely controllable. When we needed power, we can start fossil fuel based power generating sources. However, renewable energy sources which depend on solar irradiation or wind speed are intermittent in nature, and their generations vary and cannot be actually forecasted at any real time, which makes the balancing problem between load and supply more and more difficult. Uh, we assume that the electricity prices reflect the excess or deficit of power in electricity network. Such an electricity price will become more volatile with integration of greater percentage of renewable energy sources. Responsive end users can gain by altering their consumption behavior. Arbitrage implies buying a commodity when it is cheap and selling it when it is expensive. End users having energy storage can alter the manner of electricity consumption, considering variations in electricity prices to earn profit by doing energy arbitrage. The objective of this work is to find an efficient algorithm for finding optimal energy arbitrage. The system consists of a residential customer having a rooftop solar PV and battery. This residential customer is interfaced with the power grid via an energy meter. We assume non-elastic load of the end user. Based on the variations in rooftop solar, the price of electricity, and the demand of the residential customer, the different power flow cases will be developed, as shown in the slides now. So these unique power flow directions will be decided by these instantaneous parameters. Whether the battery needs to be charged, discharged, will depend on is there solar generation available at that instant, or whether the price of electricity is too high or too low at that time instant. Moving ahead, net metering compensation mechanism can be bifurcated into selling price being equal to the retail rate or below the retail rate. In the present work, we assume that the electricity price vary over time and the end users behave as the price taker. The third assumption is the buying and the selling price at any particular instant is the same, which will imply that the selling price is equal to the retail rate. Using this assumption, the mode of operation of the battery that we need to decide will only be the function of the variations in price and will become independent with the load variations. Load without having storage. So the non-elastic end user consumption minus the rooftop solar generation will not affect the optimal decisions for the battery. This is when the price of buying and selling at any particular instant is the same. You taking a numerical example, the first plot here shows the price of electricity over a day. This is a real data from New York ISO. Now our objective is to control this battery in an optimal way such that the gains are optimal. So we have the price data. Using our proposed optimal arbitrage algorithm, will take optimal decisions and maximize the possible gains. The results plotted here, the first plot shows the shadow price of this transaction at any particular instant. The second plot shows the ramp rate. The important thing to note here is the optimal ramp rates can be an intermediate value. It need not be zero or maximum or minimum value of the ramp rate. The third plot shows the optimal battery capacity. Using the proposed algorithm, we conducted extended simulations for real price data from several ISOs in US and Europe for the year of 2016. This case study is used to identify the potential of energy arbitrage in contemporary electricity market. We extrapolate the arbitrage gains for an end user for a 5-year period, considering detailed losses in the battery. We propose a mechanism to calculate the net average available capacity of the battery, considering various kinds of losses listed here. The numerical evaluation suggests that only arbitrage cannot create positive net present value for storage. This implies subsidies are required to incentivize investment. Our numerical results are evaluated for these ISOs having the pricing mechanism of real time, of time of use, and the sampling time is also tabulated in the table. We evaluate the potential, the financial potential for three different batteries. Battery with a slower ramp rate and other batteries having faster ramp rate. Battery 3 is very interesting because the potential gain is higher than the present battery cost, which is $500 per kilowatt hour. However, the operational cycle for this battery is tremendously large, which implies that using this price model, the battery will not last for 5 years. So the gains will be far lower than the gains listed here. Concluding our work, our problem formulation transforms continuous convex optimization problem into a discrete one by exploiting the piecewise linear structure of the cost function. We show that the optimal storage control decisions do not depend on prices beyond a certain subhorizon. The worst case runtime complexity is found to be quadratic in terms of number of time instants for which the price values are available. Only arbitrage cannot create positive net present value for the storage. There are three future directions that we have identified. We would like to incorporate and analyze the effect on arbitrage gains because of error in forecast and its effect on the optimal arbitrage algorithm. In the present work, we have proposed the computationally efficient algorithm. We would like to integrate this by simultaneously considering forecast errors. The second area will be the extension to the generalized analysis of unequal buy and sell price of electricity. The third aspect that we would like to analyze is, can we use this algorithm for price-based demand response? That's all from my side, folks. Thank you, and please vote for my video.